Okay, for your research projects, what you need to do is you may read some of the basic papers, especially if you read the survey paper that I referenced before. You will have access to many basic papers in network location. You may want to read a few of them to get the basic ideas. And then you should probably read a few papers that are recently published within the last 5 years or so, or last few years if possible. Because the more recent a paper, the more interesting references you will find. In fact, when you read a recently published paper, or accepted paper, it doesn't have to be published, but if it's accepted for publication, that's good enough. If you read that, normally such papers will also outline what's missing in the research. In other words, they answer a certain question, but then what is not answered is usually evident from the introductory discussion of the problem, or maybe from the conclusion. So that's the way to go about these things. Don't try to read too many papers. All I expect is really maybe not more than 10 papers or so, just covering the essentials. If you go over 10, fine. And of course, not every paper has to be read in the same level of depth. Okay? So please focus. And also, when you start doing some research and doing some reading, you should probably come and see me to discuss what you found out or what you did not, but at least come prepared. Don't come to me without having done any reading. Okay? When you come to me, I'll probably direct you to either more interesting topics that might have escaped your attention, or something more challenging. As I said, work on challenging questions, or also you may work on less challenging questions, no problem. Nevertheless, if you work on a somewhat interesting and challenging question, you don't have to really solve it. I don't expect that. But do some work on it, whatever you can. For example, work on certain examples or insightful observations, so on and so forth. Okay? So don't panic. This is not your dissertation. This is not your master's thesis. It's just a project, but I do expect you to do some work. All right, any questions on that? Everything is fine, okay. So we need to also discuss the exam time. The first, how many exams did I tell you? 2 exams? Okay, so one is final. The first exam will be somewhere either in the 6th week or later. Which takes us to the middle of where? Beginning of April? March? Well, let's make it later because, yes.
We have an exam at 6th of March. April, sorry.
April.
In the first week.
What exam is that?
Discrete optimization.
Hande Hoca's? Okay. All right, I'll do it either before or after that, okay? As I recall, I think we started out discussing the minimax location problem for 3 networks, except that I stopped temporarily and made the optimization a recognition problem, which means that when you wanted to minimize z subject to every weighted distance is less or equal that z value, So this is a weighted distance plus addend, which means z minus ai divided by the weight. This was the actual problem we were considering for the case of a tree network. Sometimes I switch to a general network as well. So z is a variable here, but if you momentarily fix the value of z, what happens is z minus ai divided by wi gives you a number, a positive number, hopefully. And that number is going to be an upper bound on the distance. So that's where we switched off. Okay? So from here, we started considering an investigation of the constraints dx vi less than or equal to ri for I going from 1 to n. Okay? So do not lose perspective. We're temporarily forgetting the optimization and we're concentrating on this problem. Okay? For given values of the radii r1 up to rn. Questions or something?
There is something. We know that when the weights are 1 and the addends are 0, we know that the intersection will be 1 point.
Yes.
Just exactly 1 point. But if the addends are positive and there are weights, will it still be 1 point, or will it still be just
a region?
Yes, a region or just 1 point?
I know the answer, but I'm not going to tell you right now, okay? Let's wait until the theory leads us to whatever the result is. What do you think intuitively? Do you have any intuition on this?
If Z is discrete, of course it will be, I guess, a region, but...
Well, Z is not discrete. Z is continuous. It's a... We're doing a continuous optimization here. In other words, Z can be any real number here. Okay?
I think a region.
He thinks it's going to be a region. Did you say 1 point? Somebody said 1 point? I thought you said that. Did you? You did say that. Okay. He thinks it's going to be a single point. How many people think it's going to be multiple solutions? Raise your hands. For a tree network or for a general network? Which one are you asking the question for?
Tree network.
Okay. For a tree network. So that's where the question is being asked. And those of you who think it will be a multiplicity of solutions, raise your hands, please. 1. What about you? Okay. 1. What about it, those of you who say it will be a unique solution? 1. What about the other people? What do they say? Nothing. You think it's going to be unique also? Okay. Well, we'll see what the answer is. I don't know. Well, I do know, but I'm not going to tell you. Okay? All right. Anyway, this is the problem, and this amounts to the following. The distance between x and vi is less than or equal to ri for a given radius ri, if and only if x is in a neighborhood of radius ri of the point vi. What's the definition of this? The definition of this is the set of points y in the tree such that distance between y and vi is less than or equal to ri. That's the definition. Okay? So you can see that there's a direct relationship, and accordingly, there's a point x in the tree such that the distance of x to every vi is less than or equal to ri if and only if the intersection of the neighborhoods around each vertex with the given radius, when you intersect them, is non-empty. I think that's an obvious relationship, but if you don't see it, please raise your hand, because sometimes things that might be obvious to one person may not be that obvious to other parties. Okay. All right. So we're investigating this now. So you can observe that the neighborhood VI-RI is a subtree, meaning that it's a connected subset of the tree under consideration. Okay? Here's an example. For example, if I sit here, if this is my V1, and if the edge lengths are, say, 1, 1, 1, 1, 1, 1, 1, a neighborhood of V1 with radius 1 is this subtree. You go 1 unit in every possible direction away from V1. And then that generates that particular set of points, which is a subtree. Okay? Of course, n can be, the radius can be fractional, say 1.5. I'm not barring that. In which case, you would extend this a little bit further, halfway here, to include the wiggly points as well. Okay? Here's a theorem which is going to be related to what we had before. Actually, I know I started out with a theorem that says that these constraints will admit a solution if and only if the distance between every pair of vertices is less than or equal to the sum of the radii between those vertices. Okay? But to get there, let's first talk about this subtree intersection property, which is a theorem due to Horn back in 1978. It says the following. Let S1, S2, Sn be subtrees of a tree T. Of course, these will be fulfilling the roles of the neighborhoods. Nevertheless, let's just take them to be subtrees. Okay? then the intersection of all of these is non-empty if and only if each pair has non-empty intersection. So this part is straightforward. Assume the intersection, say S, is non-empty. Then there's a point X in the intersection. Clearly then, X is in each SI, I1 to N, and so X is also in each intersection. Okay. When I equals J, of course, you get simply SI, so we don't have to have that. Okay? The other parts. This part is a little bit more difficult. By the way, the first part, of course, applies to general networks as well. There's nothing really mysterious about that. Okay, so in the second part, what we are going to do is I'm going to define EI to be the set of extreme points of the subtree SI. So let EI be the set of extreme points, meaning that they are the end vertices of the subtree SI. Extreme points or end vertices, end points, sorry. The points that have cardinality, that have only one edge incident of SI. As an example, for example, if you have this subtree, this is my SI, then EI consists of those points at the very ends of that subtree. Okay? All right. And let E be the union of these endpoints. Of course, you've got finitely many such points. So let's define a new point set P, which is the union of the original vertices as well as the endpoints. Okay? And take each point U in P as a vertex. The original vertices are already vertices. The new points that are extreme points are also vertices in the new situation. Okay? Can I do that? Of course. If this is a point such as this one, if it's not a vertex point, I can certainly call it a new vertex. It's an artificially defined vertex. There's nothing mysterious about that. Take an arbitrary point R in P to be the root node or root vertex and number the other elements of P. Sorry, not the other, but number the elements of P in the following way. In such a way that now what's that way? You assign the smallest number to the root node, okay? And then so root R gets number 1 as the vertex number, and any vertex in P which is not numbered yet gets the next number available. Numbers are given in the order 1, 2, 3, etc. in increasing order. So the next number available, if you've already used numbers from 1 up to k, for example, the next number available is k plus 1. Okay, so you might want to make a note of that, which is not numbered yet, gets the next number available only if all nodes or all vertices in the path connecting the root to that vertex are already numbered. So if this is the root, then you're looking at the tree in some way, and suppose this is the vertex under consideration. Then you inspect all vertices here. That one has a number 1. The other ones must have also some numbers. Could be anything, 2, 5, 8, 11, 12, etc. And then you assign the next number available, which could be 17 in this case, because other numbers will be elsewhere, okay, to this one. Okay, so that's the idea. What does that do? Let me erase that, or let me just continue here with this numbering scheme. All parent vertices have vertex numbers that are smaller than their children. This is, I'm sure you are familiar with this sort of thing from computer science. What do you call this, Pelin? Huh? There's a name for this. I forgot the name. Huh? You don't know it? Huh? Offspring? No. There's a certain term for it, but I forgot now. Anyway, you got the idea. You assume, for example, here 11 is an offspring of or child of number 8. There could be some other childs, of course. For example, that could be number 14. Again, 14 is a child of 8, and this is the parent of that. So we know that the numbering is in such a way that parents have smaller numbers than children. Their children, of course. Okay, not all children, but their children. Okay. Okay, why did I do this? First of all, let's make a definition. Let Ni be the smallest number assigned to vertices in Si. Ni is an integer, a positive integer, and it's the smallest number received by vertices in Si. Suppose you're looking at two SJs, Si and Sj. One of them has a smallest number, which is larger than the other one's smallest number. Okay. The fact that Si intersecting Sj being non-empty implies that something. It implies something.
Si. The intersection is equal to Si.
Are you sure? That would be too strong.
It's a subset of Si.
Includes? Which one? Well, that's the same. Are you sure? Well, I never thought of it that way. Maybe it is.
I minus J is... It's a subset of Si.
No.
Maybe.
I don't know. Let's look. And you don't know the answer, just draw a little picture and see what happens. Let's look at the root here. That's my R. The tree goes something like this, whatever. So let's assume, for example, that's my, and this is the larger one. That's my Ni. Let's just assume that, okay? And there's another Nj here. And I know that Si intersect Xj is non-empty by assumption, because that's what we're working on. Now, where do you think is Si? Si will be somewhere here, right? It will be a subset of the tree here. So I'm going to leave this blank, but let's just analyze this. We know Si is a subset of the subtree rooted at Ni. Ni and further larger numbers, Si is contained there. What about Sj? Sj is contained here in this portion. Now, what's the problem here? Or is it true? Can Si also be here? What about this one? Can it be? Well, if they intersect, they better, extend towards one another, right? This one is, for example, 5, or let's make it in fact larger. Let's make this 9. This one is 4. So this is numbered prior to that. What do you think?
There's at least one node in common, then there is a cycle.
There's no cycle. This is a tree.
That will be an intersection.
Well, if they intersect, either Sj extends this way or Si extends this way to include stuff here. Why Si? Okay, Si cannot extend this way. Why? What about Sj? Can Sj extend this way?
Yes.
Why? Why do you think so? Well, so the smallest is here, so it cannot. So this picture does not depict the intersection situation. That's what's wrong with the picture. So the correct picture should have Sj where? Somewhere here?
No, low that point.
Where?
It's the intersection.
Which one? This one?
Yes. That's NJ. That should be NJ.
Are you sure?
That should be NJ. And
So I see what you're saying. Yeah. So Sj will be a subset of that subtree. Okay. So we know Si is a subset of the subtree rooted at Ni, and Sj is a subset of the subtree rooted at Nj. Okay. And in order for them to have an intersection, of course, the subtree Sj and the subtree Si, the red one, they have an intersection. So what's the conclusion?
to H between these two.
The reason I was not too sure about what you said is because the red part here does not have to be a subset of the black part. Okay, over here we don't know what's going on. They don't have to be have a subset relationship. Nevertheless, the only thing we know is that this point is in fact indeed in both of them. Okay, so Si intersecting Sj implies that Ni, the larger number, is in the intersection. Okay. course, Sj might also be extended here somewhere. Whatever. Doesn't really matter. Okay? Okay, so let's see. What's the, yes? Assume without loss of generality that the smallest number assigned to the nth set is, that's a bad choice of notation, but I'm sorry, that's what happened. Nn is greater than ni for all I different from n. Okay? So in that case, what do I know? Then the last number is in all of them. It's in the intersection of all of them, or it's in Si for all I 1 to n. Does everybody agree with that? Because the largest, well, you know, it's from here. Whenever you have non-empty intersection, the larger one belongs to the intersection. And so, by assumption, this is the largest one, the one that received the last label. So it belongs to everybody. Yes?
We don't know if the intersections exist.
John, is this what you were asked to say? Yes. That's I sort of shortcutted before, but the assumption that each pair has non-empty intersection implies that Si intersecting with the nth set will have that particular vertex, which means it's at the intersection of all of them. Okay. So to establish the connection between the distance constraints and this neighborhood intersection business, let's consider a pair of constraints for fixed I and fixed j. Forget all of them. Just pick a particular pair. And state the following. There's a feasible point x that satisfies both of these constraints if and only if distance between Vi and Vj is less than or equal to Ri plus Rj. So, first, assume there's a feasible solution. Say X bar. Of course, we are in a tree network here. Consider a pair of constraints is in a tree T. Okay, please add that, otherwise things will not be true.
That intersection property also for general
Yeah, one of them will be true for general networks, but the other one will not be. So that's why I'm restricting. So let's look at this one. Assume there's a feasible solution, say X bar to both constraints. Then the distance between X bar and Vi is less than or equal to Ri, and distance X bar Vj is less than or equal to Rj. When you add them up, what do you get? Accordingly, distance X bar Vi plus distance X bar Vj is less than or equal to Ri plus Rj, because each term is less than or equal to the corresponding Ri. And what do I know about this? This is greater or equal Vi Vj. This is only using triangle inequality. So this proof is applicable to general networks as well, because there's nothing special about tree networks here. Valid also for general networks. The second part, suppose now distance between Vi and Vj is less than or equal to Ri plus Rj. I need to show that there's a solution to the pair of constraints. Anybody? Let's do it this way. Well, just think of the string analogy. You have a pair of vertices and there's a unique path connecting them. What do? You pick a string of length Ri, engage one endpoint at Vi, and pull it tight towards the other vertex along the path. You do the same thing for the other one. And if the string lengths, when added up together, exceeds the path length, then they overlap. Okay? So how do you translate that to a regular proof here? Consider the point, this is a unique point, X bar, which is or whose distance, consider the point x bar on the path, say P connecting Vi to Vj, whose distance to Vi is exactly Ri. So pictorially, you've got your Vi, you've got your Vj somewhere, and that's the point where distance between x and Vi is Ri. Okay, you stretched your string as much as that. Now, this point should be feasible to the other constraint as well. Why?
It is not that the path lengths cannot be smaller than the sum of the radiuses.
Okay, so what do we know about this path length?
This one.
Yes. Here's where we actually use the tree network property. There's an exactly one unique path between Vi and Vj, and that path length defines the distance. So since x bar is a point on that path, then of course this equality should hold true. Normally this is greater or equal, but for the case of tree networks, it's equality. That's a crucial difference. All right, so accordingly, the distance between x bar and Vj, which is equal to how much? Well, it's going to be distance Vi Vj minus distance x bar Vi. That one is greater or equal Ri plus Rj. And this one is less than or equal Ri. Because, well, actually, it's equal. It's equal. So this will be equal to Rj. So distance between x and Vj is less than or equal to. What's wrong here?
Is less or equal.
That's less or equal, yeah. That's less or equal, sorry. So the entire thing is less or equal to Rj. All right, so that's a pretty straightforward thing. I'm going to just state one theorem and then I'll let you go. Okay? distance constraints, distance x vi less than or equal to ri, I going from 1 to n, are consistent, meaning that they admit at least one feasible solution in the tree, if and only if the pairwise distances between the vertices is less than or equal to ri plus rj ij between 1 and n, which is true if and only if each neighborhood VIRI intersection with another neighborhood VJRJ is non-empty. Now, where's the immediate proof? You get the immediate proof from the lemma. The lemma simply says that two constraints at a time will be feasible if the intersection is non-empty. So this part and that part is from the lemma, the equivalence between them. And we also proved that this intersection property for pairs implies the intersection of the entire thing is non-empty, okay? So the last statement simply implies that the entire intersection is non-empty, and when the entire intersection is non-empty, then what happens? The constraints are consistent. Okay? So if you pick any point in the intersection, then, of course, because that point is in every neighborhood, it will satisfy the particular constraint associated with that neighborhood. Okay? All right, so let's just conclude it here. Next time, we will see how that actually translates into solving the minimax location problem. Okay?